welcome to this part series in which we are currently tackling the 2017 past paper in chemistry, right? And in this one, we'll be looking at question 5 as well as question 6, which fall under the topic of reactions, rates of reactions, and chemical equilibrium, with a bit of stoichiometry in between. I apologize. I am currently a little bit under the weather, but nothing to worry too much about. Let's jump into question 5. So they say a group of learners use the reaction between powdered zinc and, very important, right off the bat, excess dilute hydrochloric acid. Okay, powdered zinc Zn, dilute hydrochloric acid, dilute HCl, to investigate one of the factors that affect the rate of a chemical reaction. The balanced equation for the reaction is this. And again, lucky for you, they've balanced the equation. But had they not, you would then have to do the balancing yourself, right? They say they conduct 2 different experiments. The reaction conditions used are summarized in the table below. And they tell you that they did 2 experiments. The temperature remained the same. The volume of hydrochloric acid remained the same. The concentration of hydrochloric acid was changed, and the mass of zinc we do not know of. The results obtained are shown in the graph below. Okay, then define reaction rate. So once again, if I remember this correctly from back in the day, reaction rate is the change in concentration over, specifically in the change of concentration of the products of a reaction the products or the reactants within the reaction over time. Okay. Now we'll give you both of your marks. Let's see, let's just shift it over here, move it over there. There we go. Reaction rate. Then write down an investigative question for this investigation. Very important when dealing with physics experiments, that you develop a hypothesis or an investigative question for this investigation. Now let's go read there at the top to see what we could possibly choose for our investigative question. And we see here that, again, the temperature and the volume don't change, the concentration does, and the mass we do not know much of. So something along the lines of the change of concentration over time would suffice. So for example, you can say the change in concentration, the change in concentration of the products or reactants over time. You can say the rate of change of concentration, or you could say, the number of moles of products that are formed or reactants that are used up over time. Okay. So to give you a proper example, now bringing into consideration the fact that they they have given us um, variables to consider. We can say something like, well, what is the relationship between concentration and reaction rate? Or how does the reaction rate change as the concentration itself changes? Okay. Then question 5.3, which curve P or Q represents the result of the first experiment? Explain your answer. Now, let's just check. Represents the results of experiment 1. Experiment 1 started off with our temperature. 24. The volume is at 25 and the concentration is at 0.25, whereas in the second experiment, the concentration of HCl is 0.4. Well, very easy to see. We are looking at the example where the concentration is lower. So the volume of H2 produced, we would show the lower of the two values, or the steeper of the two values as our answer. So our answer over here would be Q. And an explanation for that is, like I said, it has the smaller gradient. It is steepest, so therefore we'll represent experiment 1. Then they say the average rate of production of hydrogen gas, as represented by the graph, was 50 centimeters cubed per second. Calculate the mass of zinc used. Okay, this is most definitely a quantitative aspects of chemical change question, or basically stoichiometry question. So I'll give you about 5 minutes to try maybe work through it, and after that I shall take you through the answer, noticing obviously the units over here, the fact that you are meant to calculate the mass of zinc used, right? And they tell you to take the molar gas volume 25 degrees times that. Okay, 5 minutes, and we shall come back and have a look at it together. Okay, hopefully by now you kind of have an idea of how to go about solving this question. And if not, I will take you through the process. Okay. And just a note moving forward, what I'll do is I'll allow you to pause the video rather yourself in order to work out a question rather than to give you 5 minutes within the video just to save time. For those that want to go through it, they'll pause the video. If not, you'll stick around and see how it's done. Okay. So, like I said, definitely a stoichiometry question, right? And just by sorry, ooh, um, wintery season. By looking at this, you have the average rate of production of gas be given to you. The problem is it is in a different format to what we need it to be. Oh, actually, no. Thing to note is you're giving in centimeters cubed per second, but the molar gas volume is also given to you in centimeters cubed. So you can actually keep it that way. Now, what you then say is, you're given that your average rate is equal to delta V over T, right? Your average rate is given as that, which is okay. So if you substitute in, you will have 15 being equal to V we still need to find, but we know that time is 30 seconds minus 0 because that's where we started at, right? And so therefore um, your volume is equal to 450 centimeters cubed. 450 centimeters cubed, right? And that would be the volume of hydrogen gas that is produced. And if you want the number of moles of hydrogen gas that is produced, you will say, well, the number of moles number of moles of hydrogen gas is equal to V over Vm, which is the molar gas constant. And if you substitute what you found so far, you will then get that the number of moles of hydrogen gas number of moles of hydrogen gas produced is equal to, and we found our volume to be 450. We were given the gas constant as 24,000, and through that you then find that it is all equal to 0, if you plug this into a calculator, 0,0188 moles. Okay. Now, due to the molar ratios over here, hydrogen gas is equal in the number of moles to your zinc. So the zinc produced is the exact same number of moles. So in actual fact, you can say number of moles of hydrogen gas is equal to number of moles of zinc in solid form, and they're both equal to 0.0188 moles. Thank you very much. From there, you can multiply it by the molar mass of zinc to get the mass of zinc. So 0.0188 is equal to the mass of zinc, which we currently are looking for. And that entire thing is all over molar mass of zinc, which is 65, and that you get from your periodic table. Substitute that into there, and eventually end up with a mass of zinc is equal to 1.22 grams. And that would have been the working out required in order to answer this question. So to reiterate, we started off with the average rate that was given to us to be 15 centimeters cubed per second. Okay. We know that this reaction took place over these time intervals, and we took the interval specifically of 30 seconds and 0 seconds where it started, and we plugged those values in, 15 for the average rate, 30 minus 0 to give us the difference in volume. We found that difference in volume to be 450 centimeters cubed. Now we took that, plugged it into the molar equation for volume, which is V over Vm. We got 450 that we substituted in. We were given the molar volume constant to be 24,000 centimeters cubed. The units cancel each other out, and you end up with 0.0188 moles, right? And we take that, we use the molar ratio that is found from the equation over here. 1 is to 1. So therefore, the number of hydrogen moles is equal to the number of zinc moles, which is equal to 0.0188 moles. Take that, substitute it into the molar equation again, this time for zinc. And because it is a solid and not a gas, we use the mass molar equation as opposed to the volume molar equation. And using that one, we have mass of zinc, which we're trying to find, over the molar mass, which is 65, which is found in your periodic table. And you take the 65 and you multiply it with the 0.0188. You get your mass in grams, which is 1.22 grams, which doesn't sound like a lot, but produced such a reaction. Okay, and that is question 5.4. I think question 5 continues. I am correct. And 5.5. In a third experiment, 200 centimeters cubed of a 0.25 moles per decimeter cubed. Now, before I carry on reading, just note over here that our concentration is given as moles per decimeters cubed, whereas our volume is given as centimeters cubed. We're going to have to perform a conversion over here. Now, the hard and fast rule is 1 dm centimeters cubed let me try that one more time. 1 mole per decimeter cubed is equal to 1000 moles per centimeters cubed. So the conversion Um, or if you'd like, the conversion between 1 decimeter cubed. Again, I'll move it up just now. Is equal to 1,000 centimeters cubed. Let's just move it up so you can see it. One decimeter cubed is equal to 1,000 centimeters cubed. Okay, and we will need to make use of that in a couple of seconds. But third experiment, 200 centimeters cubed of a 0.25 molar dilute hydrochloric acid solution at 35 degrees reacts with the same amount of zinc powder as in the two other experiments. Now, question 5.5.1. How will the heat of reaction of experiment 2 compare to that of experiment 3? Choose for more than, less than, or equal to. Well, the heat of reaction doesn't really depend on what volume or concentration is used. The heat of reaction is the heat of reaction. It's a energy value, and so will remain exactly the same. Equal to is our answer. Then, how will the activation energy of the reaction compare with those two reactions? Once again, the energy has nothing to do with the concentration or the volume. It is simply an energy related comparison, and the comparison remains exactly the same. They say the rate of reaction in experiment 3 is higher than that of experiment 1. Fully explain this by referring to the collision theory. Okay, bit of a mouthful, but basically the collision theory is the idea that with a greater number of moles or a reduced volume, more collisions will happen, which will affect the rate of reaction. Okay, basically the idea that there are four different categories that will result in the change of rate of reaction. And those are concentration, the amount, a catalyst if it's used, the pressure, which is related to the volume, temperature already mentioned, and concentration. Okay. So if you have to fully explain this by referring to the collision theory, basically, given the fact that experiment 3 occurs at a higher temperature, the average rate of, or the average kinetic energy, which is related to the temperature, would be higher. Higher temperature, higher average kinetic energy of the particles. What do we mean by that? The movement of the particles, the average movement of the particles would be higher. If they move much more or much faster, then more molecules will have enough kinetic energy to reach the threshold of the activation energy. The activation energy being the energy required in order to be able to react or to be able to participate in the reaction, right? And if we have more of these particles reaching activation energy and being able to react, well, more effective collisions will happen per unit of time, and as a result, we will have a greater rate of reaction. And hopefully that makes sense. Okay, if you think of, if you want to make the analogy that these are representatives of people in a room, well, if you incentivize everyone to move faster, or you get everyone excited to move faster, they will collide with each other or they will interact with each other much more. And if they interact with each other, you increase the number of interactions, and so therefore the rate of interaction will increase. Normally, that's how I will think of such questions, and it makes it a lot easier. So if you think of them, if you have a struggle, try to think of them in that sense. Okay, let us look at question 6. Question 6 is a chemical equilibrium question, dynamic equilibrium question, and let's have a look. Seems like there are just 4 questions to it. So much shorter than question 5. And yeah, let's have a quick tackle at what it has in store for us. Yeah, carbonyl bromide, COBr2, decomposes into carbon monoxide and bromine according to the following balanced equation. Yet again, very lucky for you, they have balanced your equation. Now, if you look at this equation, our delta H is greater than 0, was positive, and as a result of that, we are looking at a case of a endothermic reaction. Endothermic reaction, if you remember, is one in which the energy of the reactants is less than the energy of the products, or basically the system gains energy in as a result of the reaction as opposed to losing it, okay, which would be an exothermic reaction. Cool. Now moving on. They say initially the carbonyl bromide is sealed in a 2 decimeter container and heated to 73 degrees Celsius. Let's just highlight those values, very important. Okay. Originally sealed 2 decimeters cubed container and is heated to that temperature. The reaction is allowed to reach equilibrium at this temperature. The equilibrium constant, or the Kc value, which is what the equilibrium constant is referred to as. Kc value for this reaction is said to be 0.19. Okay, let's just dissect that very quickly. We know that Kc is given as the concentration of products over the concentration of reactants, right? Equals Kc. Now, when given a value that is smaller than 1 but greater than 0, it would therefore mean that our denominator is greater than our numerator, or the energy of our reactants, or the concentration, of our reactants is greater than that of the concentration of our products. Keep that in mind. Okay, in this specific case, for our products, we are looking at concentration. Just give myself a bit more space. We are looking at the concentration of CO, like that, and we are multiplying that with the concentration of Br Br2, like that. Okay, and that is all over the concentration of CO Br2. Okay, Excuse the writing. But okay, concentration of our products being placed over the concentration of our reactants, right? Coming back over here, they ask us to define chemical equilibrium. And very simple definition of chemical equilibrium is the stage of a chemical reaction at which the rate of the forward reaction is equal to the rate of the reverse reaction. All right, this out very quickly. Okay. Again, just to reiterate, the stage of a chemical reaction where the rate of the forward reaction is exactly equal to that of the reverse reaction. Okay, where the concentration of the products remains the same as the concentration of the reactants. Okay, call it dynamic equilibrium. Now, we say at equilibrium, it is found that 1.12 grams of CO, carbon monoxide, is present in the container. Okay. um, calculate the equilibrium concentration of carbonyl bromide. Okay. That right there is most definitely, obviously, a ice table question to do. And let's try to tackle it quickly. And to start things off, well, let's give ourselves some space and let's just set up our table over here. Okay, so let me just start off by doing that. Maybe zoom out to give ourselves just that extra bit of space. Okay, make this a bit bigger that way. And well, ice tables will always have the reaction itself to start off with. Then we will have a couple of columns, one for every letter. The first one, I, referring to the initial quantity. C, referring to the change in quantity. And E, referring to the equilibrium concentration. Okay, I've added an extra compartment just for the reaction that we are about to add over there. Okay, just add this over here. Initial. Okay, initial, all in moles. We have the change, that'll also be in moles. And that for me is really the golden row. I tell you why. It is the golden row, and that's because that is where our mole ratio will come into play. That's actually why you need to balance the equation to start off with, okay? Because the golden ratio will come into play over there, right? Then over here, let's just say we'll have our amount. Yeah, let's call this our equilibrium. Equilibrium amount. This will also be in moles, right? And one more for our let's say C equals N over V. I'm actually going to need more space over here. Going to need to add one more compartment. Let's see how well we can add it over. It's pretty good. Pretty good. Just add one more line over here. And this will be our equilibrium concentration. Equilibrium concentration. And this will be in moles per decimeter cubed. Okay. And just to save time, I'll write it like that. But, I hope you understand what it's actually supposed to look like. Let's give each other a bit more space. There we go. Yeah. Cool. Time to add our formula. We have COBR2 okay. And give each other more space. They always say that engineers are not architects. I'm learning this the hard way. I'm an engineer by profession, and architecture is really not my thing. But regardless, here we are, and second of our constituents will be CO. The third of our constituents will be Br2. There we go. Okay, I can finally start adding numbers to this. Okay. Well, we know for sure that in the beginning there was no carbon monoxide, there was no bromine. Okay, so you can add zeros over there. We don't really know for sure what our initial number of moles of COBr2 is, right? But what we can at least note for ourselves, actually here on the side, is our volume is equal to 2 decimeters cubed. Okay, 2 decimeters cubed. What else do we know? We know that at the end of things, we will have 1,12 CO present in the container. Okay, now if you plug that into the molar mass formula, let's just do that quickly. N equals m over m. Okay. N equals m over m. Which is therefore equal to N equals 1,12 over, and for carbon monoxide you have 28. So plug that over there, and if you put that into a calculator, you end up with 0,04 moles. Okay, what are we going to do with that? Well, we know that, again, we know that at the end, we are going to end up with 0,04 moles. Okay, what are we going to do with that? Well, we now know that our change in the number of moles for carbon monoxide, must have been that 0,4. Okay, and specifically it was added. Now that we've entered the golden now that we've entered this golden row, okay, remember I said to you, we call it the golden row specifically because in the fact that once we enter it, we only need one value in order to find all of them using the mole ratio. So according to the formula over here, 1 is to 1 is to 1. So if you have 0,04 as your change in CO, well, guess what? 0,04 will be a change for BR, and 0,04 will be a change for COBR squared. COBR2, sorry about that. Then once you have that, well, the change will be the same and you'll end up with the same value for BR. But for bromine, because you start off with 0, you added 0,04, end up with the 0,04 moles at the end. Okay, now we can carry on a bit further. We can take the 0,04, and what we'll say is 0, the concentration is equal to 0,04 divided by that 2 moles per decimeter. We'll just do this to help you out. What I'm saying essentially is okay, is what we have over here, and exactly that is what we have over here as well. Oops, moving the wrong thing over here. Moving the wrong thing again. Eventually should let me move the right thing. Nope, it won't. There we go. Okay. Now, as a result of that, then the equilibrium constant or the equilibrium concentration for both of these guys is equal to 0,02, and over here 0,02. Okay, still don't know much about COBR squared, but no problems. That's exactly what we're supposed to look for by the end of this question. So far what we can do is take these values, substitute them into this, and see how far we get. So Kc is equal to, as a fraction, you have at the top CO and Br bottom. We have CO Br, right? That's what we have over here. And once you substitute in values, you have Kc, which is equal to 0.19, right? They gave that to us. We have 0.02 at the top because both of them have the same value. We can just say that it is squared over concentration of CO Br 2. Okay. And if you plug that into your calculator, you end up with the fact that concentration of CO Br 2 is equal to 2.11 times 10 to the negative 3 moles per decimeter cubed. Final answer. You just show that over here. Yeah. Final answer. The concentration of COBr2 is 2.11 times 10 to the negative 3 moles per decimeter cubed. Okay. And in order to answer that, we needed the ice table. And yeah, there's our answer. Cool. Then they say find the percentage now of that at 73. Percentage of COBr2 that decomposed at 73 degrees. Okay, well, stoichiometry again. The number of moles of CRB to the 2 we know is equal to 2.11 times 10 to the negative 3. Now multiplied by 2, which is the volume, right? Equals, and if you need to, I mean, it's equal to C times V. Okay, it's equal to C times V. And that entire thing is equal to 4.22 times 10 to the negative 3. Okay, just doubling the value. Nothing hectic over there. And from that, we will be able to find the initial number of moles. And the initial number of moles should be that added to the 0.04, which is the change. Remember, we had found the change to be 0.04. So if we add that to the change, say 0.04, which we found, plus this 4.22 times 10 to the negative 3. Okay. Which basically essentially equals 0.44. Okay, and that's the final answer to that. So the percentage decomposed, is equal to the initial over the total, or basically is equal to 0.04, sorry, which is equal to the change over the initial, right, times 100 is the formula. And just to save time, is therefore equal if you plug it into a calculator, 90.46%. Okay, 4 marks given to you. Then, which one correctly describes the Kc value when equilibrium is reached at a lower temperature? Now, for a endothermic reaction, if you find the equilibrium at a lower temperature, that would mean that if you find it at a lower temperature, that would mean that the Kc value must be greater because you'd end up with more product for lesser reactant. So therefore, our answer in this case would be this over here. Okay, then last question. My bad. Now that I think of it again, sorry, absolutely apologize. It would be this, because again, given that it's endothermic, a decrease in temperature would favor the exothermic, so therefore would favor the reverse reaction. And given that it would favor the reverse reaction, you'd end up with more product and you'd end up with more reactant and less product, and therefore the Kc value would decrease. 6.4. The pressure of the system is now decreased by increasing the volume of the container, and the system is allowed to reach equilibrium. How would the number of moles of carbonyl bromide be affected? Choose from whether it increases, decreases, or remains the same. The answer over here is decreases. And the reason for that is the fact that a decrease in pressure will favor the reaction that has the larger number of moles in gas. Now, in this case, you have 1 plus 2 moles in the product side versus 1 in the reactant side. Okay, you have 1 over here, and you have 2 on this side. Okay, and as a result of that, well, given the fact that that will be the case, the forward reaction will be favored, as that is the side, as the left side is where you have the lowest number of moles. So therefore, you would have a decrease in the number of moles of COBr2. And that is the end of 6.4. Practice your stoichiometry, know your ice tables, and be able to consider the differences in Kc value. Other than that, I shall see you in the next one. A great rest of your day, and cheers.